This is a table from your textbook. It's an abbreviated list. It's the ones that you'll use most often in class. Really, if you have this table and the table I show you on the next page, that's usually sufficient. And once again, this is out of the Nielsen book, chapter 12. You can see that they very clearly state that this is for a function that is defined only for t greater than or equal to 0 minus. As I said in the first lecture, some books will use this 0 minus terms, others will just say greater than or equal to 0. It just depends on how mathematically proper the particular textbook author is trying to be and whether or not it's in the context of a circuits class where it's sort of implied. Other people will, in the function, list this to be multiplied by u of t. So you either have to have this statement or you have to multiply these functions by u of t because this is a single-sided transform. This is also a list of additional transform properties, which your book refers to as operational transforms, and they give you a good list of all of those properties that we discussed in the previous lectures on Laplace. This is also from your textbook. It is a number of useful transform pairs, and you'll find as we begin to discuss the inverse transform, this table is pretty useful. So k is always a constant in 1 and 2. In 3 and 4, it's a complex number, so it has a magnitude and a phase, and that's given here in this explanation. Now we'll get to this because there are a couple of different ways to handle this kind of situation, and I'll discuss that more as we go through this lecture and some of the examples we'll do in class, as well as some of the things we will illustrate on MATLAB. All right, so as we talk about finding the inverse transform, we're going to make a couple of assumptions. So the first is that your function in the S domain is of some form. It's a rational function. You have a polynomial in powers of S in the numerator and a polynomial in powers of S in the denominator. And so the first thing to talk about is that in the numerator, the roots of that polynomial are referred to as the zeros of f, and the roots of the denominator are referred to as the poles of f. So it is the poles of f that determine the basic functional form of the response. Is it going to be sinusoidal? Is it going to be, a constant? Is it going to be exponential decay, a number of different exponential decay constants? That's all determined by the roots of the denominator. The numerator more gives you things like what is the relative contribution of each of those functional forms to the final result. So we can tell what kind of response a system represented by a differential equation in f of t, we can tell what kind of response that system is going to have by looking at the poles or the roots of the denominator. So as you know, the previous example where I looked at a particular differential equation, it does not come out in a form that you can conveniently find usually on these tables. So you don't get nice, k over s plus a most of the time. So what that means is we have to do some algebraic manipulation of the function in the Laplace domain in order to find out what are terms that we can look up on the table. And we're going to do that using partial fraction expansion. So the steps to find an inverse Laplace transform are first to decompose f of s into simple terms using partial fraction expansion, and then to find the inverse of each term by matching entries in table 15.2. So a couple of comments. First of all, the order of the numerator will need to be lower than the order of the denominator polynomial. If it's not, you will have to do long division. If you're doing this by hand, you'll have to do long division in order to reduce it to the point where it is so. Secondly, you can't have any other functional forms. So, for example, you could not have in the numerator an e to the minus 2s multiplying the polynomial. If you do, you have to pull that out and then work with that after you've done the partial fraction expansion. So what you're doing a partial fraction expansion on has to have a numerator polynomial in powers of s and nothing else. No irrational terms, no 1 over s's, nothing like that in the polynomial. So positive powers of s. The denominator has to be of higher order and also have polynomial in s, powers greater than s to the 0. So you want to, when you do this, you want to arrange your polynomial in decreasing order, and you want the denominator polynomial, the highest order in s term, to have a coefficient of 1. That's going to allow us to do what we need to do to analyze this in Laplace. All right, so first we want to talk about just polynomials in general and go over some kind of basic algebra theory that some of you may or may not remember. So when we have a polynomial, there are 3 different kinds of roots. 4, if you count 0, is a different type of root, but we're going to treat 0 like a distinct real root. So in other words, when you factor a polynomial, you can get roots of that polynomial that are distinct and real. You can get roots that are repeated, so like s plus 2 quantity squared would have a double root at minus 2. Or you can get roots that are complex conjugate pairs. And that's really it. A root at 0 is usually treated like a distinct real root. So, for example, the term 1 over s, that would be a pole at s equals 0, and it's treated usually like a distinct root. A complex conjugate pair can also be a higher order or repeated root. So I'll refer you back to this table. If you look at number 4, in this case, you would have not just complex conjugate pair, but you would have each term would be squared. So that's possible as well. All right, so basically you're going to take your denominator, because that's going to be kind of the significant thing that determines the functional form of the response, and you factor that into its poles. So what we're going to look at first, we're going to look at roots of each type. And we're going to start if you only have real roots. So this denominator is going to factor where your p's, they're referred to as simple poles. None of them are repeated. So this would be like p1 equals 2, p2 equals 4, p3 equals 5, and so on. And usually they are negative. In fact, if they're not negative, you've made a mistake. So p1 would equal minus 1, p2 would equal minus 4, p3 would equal minus 5, and so on. And you also assume that none of them are repeated, so they're all simple roots. If that's the case, and if the degree or order of the numerator is less than the degree or order of the denominator, the partial fraction expansion becomes really simple. It's going to take this form where p are your poles, and they're actually, so this would look like s plus 3, and the root would be minus 3. So it's going to look like that. So these are all like sums, which makes, and the p1s, p2s, and p3s in this expression are positive numbers. So it'd be like s plus 2, s plus 3, s plus 4, and so on, which makes the poles negative, because in order to get this to go to 0, that'll happen when s is equal to minus p1. So hopefully that makes sense. If you don't have that, you don't have a stable system. And in circuits, we assume all of our systems are stable, or else they're going to blow themselves up. So if you have a sum like this, and the p's are positive numbers, then basically you have a general solution that looks like this, where you have each one of these, you take the inverse transform, and you get this decaying exponential. And the decay rate the decay rates are the poles. So you have some constant k1 times e to the minus p1t, and so on. And then that whole thing has to be multiplied by u of t, because remember, the function is not valid for t less than 0. So that's what your general solution is going to be like if you have a polynomial with simple real roots. So if I gave you something like a function is s over s plus 2 times s plus 3, what kind of time response does it have? Your answer would be a sum of exponential decay functions with 2 different decay rates. Oh, and by the way, from this, the time constant tau 1 would be 1 over p1, tau 2 would be 1 over p2, and so on. So you could write this as time constants, but we actually don't in this portion of the course because we're going to use the poles in some plots and some additional analysis. So we just usually keep it in this form. Okay, so you can also have, the second possibility is that you have real and repeated roots. So this would be where you had some s plus p to the n, could be squared, could be cubed, could be, any number of things like that. And so if you do have that, and if it's repeated n times, then your partial fraction expansion looks like this. So you have one term with a constant in the highest order. So let's say we had s plus p to the 5th power. Then your first term would be a constant over s plus p to the 5th. Your second would be a different constant over s plus p to the 4th. Your third would be a different constant over s plus p cubed, and then so on, going all the way down to where you have just a first order term. And then this f1 of s represents are there additional terms in the function f of s. So in other words, a lot of times you'll have, if you remember our differential equation example, we had one term where we had 2 second order polynomials multiplied together. So if you have that kind of thing, then you often will have an additional function in addition to your term that is repeated poles. And we'll see actual examples of this as we work through this. If you have this situation, then the response looks like this. So when you take the inverse transform, you have, first of all, so p is your root. So you have, first of all, a constant times just a simple exponential decay. And then if n was equal to 2, you would have another constant times te to the minus pt. And if n was equal to 3, if it was a third order, you would have this additional term in t squared. And you continue until basically you reach the nth term, whatever that was. So if it's a 5th order, you would have 1, 2, 3, 4, 5 terms in your sum here, and then whatever the inverse transform of whatever else was left in the function. So real repeated roots give you exponentials times a polynomial in t. So this would be, a constant, this would be a ramp, this would be a parabola, and so on. So the third option is that our roots would form a complex conjugate pair. So once again, we're assuming that we have done some partial fraction expansion. So we have, in addition to f1, which is whatever's left, we're going to have at least one term that looks like this, where this denominator cannot factor into real roots. So one of the ways that I work with this is, as opposed to utilizing what's given in the formula in your textbook, given a function like this, I basically complete the square. So here is an explanation of how to complete the square. So what you have to live with here is you have to live with the AS term. You can't really play around with that. So what you say is, okay, let's let this term look like the middle of a perfect square. So we got 2 alpha s, where if we had a perfect square, this would be it. So basically, a in this first part in my denominator is 2 alpha s. And then alpha squared plus beta squared, in order to make these equivalent, has to be b. So you take a and you make it 2 alpha s. Figure out what alpha is, square it, and then figure out what you need to add to get to this b. Now I will say, if it turns out you have to subtract something, then you've taken the wrong approach. So it's always going to look like, once you complete the square, it's always going to look like this if you've done it correctly, and you'll have a plus sign here and a plus sign here. If you get a negative sign here, what that means is this denominator would have factored into real distinct roots, and you need to go back and refactor it and be sure you didn't make an error. Okay, then you work a little bit with the numerator. This is kind of just a little bit abstract because they're not using numbers, and so we'll see some examples where we actually use some numbers. I think it's a little easier to see it that way. But basically, you're going to have to split this numerator, because what you want is, once you have the denominator looking like this, that's an exponentially damped sinusoid. And the question is it sine or is it cosine? And the answer is, well, that depends on what the numerator looks like. So in the numerator, you want an s plus alpha term if it's cosine. You want a beta term if it's sine. So what you have to do is you have to split the numerator up algebraically so that you get one that looks like s plus alpha, you get another one that looks like beta, and then your job is to solve for these constants a1 and b1. So once you do that, then it's very easy to look it up on the table and take the inverse transform, and we'll get these two terms for the first two terms, and then whatever was left in the function that we were taking the inverse transform of will transform into whatever it transforms into. So that's the complex conjugate pair example. Okay, I want to stop at this point because the video will get kind of long if I continue to go through some of these examples. I guess I could do this one really quickly because this one's not too hard. So this is an example of how you do partial fraction expansion for a function f of s that has simple, real, distinct roots. So we have this function here, and the first check that we do, unfortunately, the denominator has already been factored for us, so we don't have to do that step. If this denominator was not factored, before you can solve this, you need to factor it, because that's actually what tells you what kind of roots you have. So we also check to make sure the numerator is of higher order than the denominator. And by the way, when this denominator was factored, the highest order term would be s cubed, and that would be multiplied by 1. So that's kind of how you need to manipulate the function to get it to this form. Now once we have it in this form, what we're going to do in partial fraction expansion, and I'm sure most of you have seen this, so I'm going to go over in kind of a pretty fundamental way what you do here, but I'm sure most of you have seen this. We assume that at some point this function was written like this. And what we did was we found a common denominator, which would be the product of all three of these, and expressed it like this. And so what we actually are starting with is the answer, and what we want to go back to is what three terms generated our answer. So we do that by just letting the numerators be unknown. So we have a over s plus b over s plus 2 plus c over s plus 3. And we assume that these two are equal. So if you assume that and you multiply both sides by the denominator, you get an expression that looks like this. And so the goal here is to find out what are a, b, and c. And the thing to realize algebraically is that this equation has to hold true independent of the value of s. So what you do is you pick two convenient values of s that make a lot of stuff drop out. And typically, if you have non-repeated roots, the easiest thing to do is to pick the poles. So if we let s equal 0, then you can see these last two terms cancel out. It's very easy to solve for a. If we let s equals minus 2, it's very easy to solve for b. If we let s equal minus 3, sorry, it looks like this needs to be an s. If we let s equal minus 3, then c is equal to 7. So then you substitute for a, b, and c, and it looks like this. And then you take the inverse transform. And so what you find is you have one term that is a step, one term that is an exponential decay with a decay rate of minus 2, and another term that's an exponential decay with a decay rate of minus 3. And then if you look at these constants, the minus 8, the 7, and the 2, that's what came out of the numerator. So the denominator, when you factored it, gave you this form that you would have two different exponential decays and a step. That came from the fact that you had an s, a root at 0, a root at minus 2, and a root at minus 3. The numerator determined what these numbers were. So if we'd had a different numerator, we'd get numbers that look very different here. So this makes your answer look quite different, but your functional form is independent of what the numerator was. So you're still going to have the u of t, the e to the minus 2t, and the e to the minus 3t. All right, now I'm going to stop before we do any additional examples, and we'll pick this up with an additional either video or lecture in class on Friday.